Last in this unit, Unit 5, we talk about recursion with logistic functions. The way that I introduce this to the kids is because we've already talked about exponential regression. Now I want to look at how exponential equations or exponential regression truly operates in the real world with some minor exceptions. Here we have the 4 stages of growth. We have the initial stage, the exponential stage, dampening, and equilibrium. Now the reason I say that this is how exponential functions operate in the real world is because rarely is there an unlimited ability for something to grow. When we talk about growth, we talk about reproduction in some animals or in the growth of the population for humans. We talk about growth of some kind of bacteria in order to generate some medicine that counteracts that bacteria. We talk about the growth in money. We talk about the growth in very many other things, and all those things for the most part have some kind of limitation, some kind of thing that's going to cause it to level off and stop growing at the exact same rate, or to grow at that rate, however, inside of some defined criteria causing it to level off at this equilibrium stage. So when we talk about or create logistic function equations and problems for our students to try to solve and analyze, the things that we need are the growth rate, the optimum living conditions, and the available space. That's going to allow us to calculate what I like to call our limitation, or on that 4 stages of growth where the equilibrium occurs. This is also known as the maximum sustainable growth. But I like to call it limitation because saying maximum sustainable growth 1,000 times in 4 different classes is going to get old. So limitation. It's also easier to write it in the formula whenever they have to put it in their notes. So here, this gives us the recursive rule. Now we might want to write that down. This is the recursive rule for logistic functions in this scenario. I don't like to do the explicit function rule for logistic functions because it is something that the students are going to just be overwhelmed with, in my opinion. And matter of fact, sometimes I get overwhelmed with it. But doing the recursive rule is much more succinct, and they can find the first few years of growth, and they have proven to me that they have been able to operate with this rule. But the recursive rule, the next term requires the growth rate as a decimal divided by the limit times the previous term times the difference of the limit and that previous term. And then we have to take this, which is called the difference equation, and add it back to that original term that we began with. So here in just a second, we'll take a scenario and I'll show you how to operate this recursive rule for a couple years' growth. So we have a problem. Now I've listed the information that we need in bullet style. However, you're probably going to write it in paragraph style because that's more real world and how they're going to approach the information. However, we have tigers that reproduce at a rate of 35% each year. Tigers thrive when there are no more than 2 tigers per 5 square miles. And then we have a 5,000 square mile ranch that's dedicated to reviving the population of these tigers. So we first need to calculate our limitation and then write our recursive growth rule. Our limitation is found by taking the number of square miles times however many tigers thrive divided by how much space those tigers thrive in. So I'm going to say that my population is going to get no bigger than 2,000 tigers. So here we have our limitation. And now we can write our recursive rule for this scenario. So when we write our recursive rule, we have our growth rate is 35%, however we need it as a decimal, so 0.35, divided by our limitation, which is 2,000 tigers, times the previous term of the sequence, times 2,000 minus that previous term, and then we need to add that previous term to what we get. Now one thing we didn't show here is that we're going to begin with ten tigers. That means our sequence is going to begin with 10, and we need to then find the next term. So when we operate with this recursive rule, we have to take what we start with and substitute it in to a sub n in order to get the very next term. So this here is a sub 1, which means we're looking for a sub 2, which says a sub 2 equals the growth rate divided by 2,000 times a1, which is 10, times 2,000 minus 10. That's the difference equation, and then we have to add that back to our a sub 1 in order to get year 2's growth. When we calculate a2, we are going to get 13.48, which tells us the second term of our sequence is 13.48. Now, the discussion that typically ensues after something like this is, how can you have 0.48 of a tiger, 48% of a tiger? I always like to come up with some random ways that we can account for almost half a tiger. I like to say that maybe one tiger is pregnant, and we're taking into account that there is one tiger that is halfway in her pregnancy phase and about to have a tiger soon, but that won't occur until the next year. I also sometimes give them the opportunity to where when they list this, they can round just to make the mathematics easier as they keep going. And it's justifiable that if we have 13.48 tigers, we don't even have the ability to round up. So we basically just have 13 tigers, and we really only have 3 more tigers that next year. So I give them the opportunity, I open that dialogue to allow them to explain what this 0.48 means, or should it even be there. And then when we use this to find the next year's growth, we have a sub 3. And in order to find a sub 3, we got to use a sub 2 and input that into the formula. So here we have 13.48, every place where just before we had 10. And so when we put this into the calculator, now hopefully your students understand how to properly put this in the calculator all at once, so it just calculates out a nice clean answer. And for a sub 3, we're going to get 18.17. And so now I have 2 years of growth of this project of revitalizing this tiger population, and then I can find the fourth year, or the third year, the fourth year, and so on, and use it recursively. Now, if you want the students to see this, I recommend using a spreadsheet software, putting 10, and then calculate the next year's growth, the next term, by using this formula. Use spreadsheet software to then generate 75 or 100 different values, because using this 100 times is going to take forever. But if you can show them how to do it in a spreadsheet software, or do it for them at the beginning of class or in the front of the class, then you'll be able to show them how this data begins to rapidly increase, and then it will level off in its equilibrium at around 2000. And you can show them how this recursive rule will do this type of model. And that is recursion with logistic functions.